Okay, so in the last section, we looked at how the multi-layer perceptron sort of fits together. And we said that there were two issues. One was working out the topology, and the other part was working out how to set the weights. In this one, we're going to be looking at how to set the weights. And the way that that was done is by the famous backpropagation algorithm. So backpropagation is one of the most simplest and straightforward ways and most general ways of finding the weights for a multi-layer perceptron. There's other ways as well. So we saw how we could set the weights in a single layer perceptron by minimizing the sum of squared errors. And we're going to do the same thing in the multi-layer perceptron, except that we're going to propagate the error backwards through the layers of the network and then change the weights based on their contribution to the error. It's called credit assignment. We're trying to look at the weights and we're going to say you're the one to blame for this error, so we're modifying the weights for the weight according to that credit that we assign. And the way that it works is like this. We start with an untrained multi-layer perceptron. Okay, that means we start with a multi-layer perceptron with small randomly set weights. Usually they're often in between plus and minus 0.2. So little uniformly randomly generated numbers. So we start with an untrained multi-layer perceptron. We're going to present the patterns to the multi-layer perceptron, and we pass the pattern through the network to calculate the network outputs. So it's the feed forward, like we showed in the last part of the lecture. We feed the inputs through each of the layers of the network, and we calculate the network output using the approach we were using before. Then we're going to compare the target values. So we look at the output from the neural network, we compare that to the actual target value that we want, and the difference is the errors. And that error for the network is some function of the weights, and it's minimized when the multi-layer perceptron produces the correct output, i.e. when the weights are set to the correct values. So we're going to adjust the weights in each of these times of showing the patterns to the network to reduce that error, and then we're going to work out the error and propagate that backwards through the network. So each unit or neuron in the neural network computes a weighted sum like this. So the activation of neuron J is the sum of the weights from neuron I into J times the input into the neuron the input I into neuron J. Let me say that again. The activation of neuron J is summed over all of the inputs into neuron J, all of the I's. So the weight from input I, the weight for input I to input J times the actual input from neuron I, and that's Z. Notice that the W sub Ji is a little bit different notation to previous, and it is a little bit weird. So Wji is the weight from neuron I going to neuron J. It's sort of backwards to what you would expect, but it's commonly used in the literature. So once we've got this activation, we transform it using some nonlinear activation function. So we've talked about that as the sigmoid, but we're going to just use the general case G. So the output of neuron J, Zj, is equal to the activation function G of the activation into neuron J, Aj. So the Zi's in that first line of maths could be inputs, in which case we'd replace those with x's, of course, because they're the inputs, and unit J could be an output, in which case the A would be a Y. So we've got our activations and our outputs of the neuron. Now we're interested in the error measure. So the error measure is going to be a function of the weights, and it's going to be we're interested in the error for pattern N, and we're going to sum up the error for each of the patterns and that's going to be the total error. So we want to, and the error for pattern N is going to be a function of each of the output neurons. In this case, we have C output neurons. So we want to calculate the derivatives of the error with respect to the weights and biases, because that's going to allow us to assign the error to each individual weight. So this is the credit assignment issue. And we're going to consider each of the errors on each pattern separately. So we can define the training error like this. So the training error on pattern N using a particular set of weights is defined as TK is the target on output neuron K minus the ZK is the actual output from the network. So we're going to square that and then sum that over all of the output neurons, and then we'd take the half of that. So that's essentially the T is the target vector we're trying to produce, Z is the output vector of the neural network, and then we take the square norm of that, and we use a half of that. That's just to make the maths work a little bit better later. So K is going to iterate over the C output neurons, T is the target pattern, Z is the output pattern, and the backpropagation algorithm that we're going to use is based on gradient descent. The idea is the weights are initialized randomly, and then we're going to change them in the direction that will reduce the error. So we've already seen that before. It looks like this. Remember that? So here we've got, this is what we saw before. We start with random value of W, we change the weights a little bit in the direction that minimizes the error, using eta, which is the learning rate. So we're going to use exactly the same idea here for the backpropagation algorithm. So going back to what we had before, the top part we've already seen, that's our error for pattern N, and backpropagation's based on gradient descent, so we need to have some weight change. So the delta W, the weight change, is minus eta, so the learning rate, times the partial derivative of the error for that pattern N given the weights. We normally want to do it for each weight, so we get this part on the bottom right. So the changing weight for the weight going from neuron Q to neuron J is minus eta, the learning rate, times the partial derivative of the error with respect to that particular weight. So eta is the learning rate, and we're going to update the weights in the following way. So the weight becomes the old weight plus this delta weight. We're going to do that for each pattern until the multi-layer perceptron gives us small enough error. Okay, so we're not going to look into how we calculate that change in weight as minus eta times the partial derivative of the error with respect to the weight. We're not going to go into that in detail, but we do need to consider the weights that go into the output neurons and the weights that go into the hidden neurons separately. There's a really nice piece of calculus that essentially just uses the chain rule to calculate these. And if you're interested, I really urge you to go and chase up, because it's really quite nice and it's reasonably easy to calculate. But we're going to skip all the calculus. So this is the answer. So skipping all the calculus, the way that we want to update the weights is as follows. So remember, we've got our weights. Our new weight is the old weight plus the delta W. And for the delta W, if the weights are going into the output neuron, then we do it this way. So the change in weight from I going into J is eta times this thing called the sensitivity. That delta J is the sensitivity of neuron J. It measures how the overall error changes with respect to the neuron's activation, net activation. And then we've got eta times the sensitivity times yi, which is the output. And that's just defined as, if you go through all the calculus and work it out, it's eta times the difference in the target value for neuron J, output neuron J, and the output of ZJ times the derivative of the activation function, so that's the first derivative of the sigmoid, of activation J times Yi. And then for the weights going into the hidden neurons, the change in weight for the weight going from neuron I to neuron J is again eta times xi times the sensitivity of neuron J. And if we calculate that all out, it turns out that it's eta. So instead of the target minus the output, now we need to look at the what's coming in from the hiddens. So it's the sum over all of the neurons coming into J. No, it's coming from J. So J into the other neurons times the sensitivity of that, and then again we multiply by the derivative of the sigmoid function if we're using sigmoid, and the activation function itself times xi. Looks complicated, but you can plug all of this quite nicely into a little program, and you can write code to do the neural network. Again, I'd urge you to do that if you're interested. It's really fun to write this stuff up and then see it working. So we've got our algorithm for setting the weights. We know how to set the weights. It's a little bit different depending on whether we're looking at output weights or weights going into output neurons or weights going into hidden neurons. So now we need to think about how we're going to stop the training. So a lot of methods just run it for a fixed number of epochs. So an epoch is you show all of the patterns to the neural network. So going through all of the patterns in one go is one epoch. So sometimes people will stop after, say, 100 epochs or 200 epochs or 1,000 epochs. A better way to do it is to use a training set, a test set, and a validation set. So the idea is similar to the way that we've used these data sets before. The neural network is trained on the patterns in the training set. So the weights are changed based on that one. The training should stop when the error on the validation set starts to increase. And then once we've stopped the neural network training, then we can quote the error on the separate test set. So it's this same pattern, same kind of thing that we've seen before. So as we train it for more and more epochs, the error on the training set decreases, and the error on the test set starts to decrease. But eventually, once you've trained it for long enough, the error starts to increase because now again the network is starting to fit to the noise in the data or the idiosyncrasies in the data. So this version of backpropagation, despite the calculus that I guess was a bit complicated, is the simplest version of backpropagation. However, it turns out it's quite slow to train the neural networks in this way. So over the years, many people have come across different ways to speed up backpropagation and get better results and to get better convergence. So people have tried lots of different things. They've looked at separate learning rates for each neuron, or they've changed the learning rate as the learning progresses. So when it's looking at smooth parts of the landscape, it can use big steps. When it's a very curvy weight space, then it needs to use smaller steps. There's one commonly used improvement called momentum, and I'm going to go through this because it's used a little bit in the software. So the idea is to add inertia to the movement through the weights. So the weight update that we saw before was delta W is minus eta, the learning rate, times the partial derivative of the error with respect to the weight. When you add momentum, you add another term. So it becomes the change in weight is minus the weight change that we had before, that we calculated for this pattern. But then we add mu, which is the momentum control, times the weight change that we made in the previous step, or maybe the previous epoch, depending on how we train it. So there's a weight change we we would take for this step, but we keep going a little bit in the way that we were going previously. So the idea is, and so your mu will usually be a number between 0 and 1. A bit like your learning rate, that's eta is usually a number between 0 and 1, typically less than 0.3. So the idea is that when it gets into a point, it'll stop it fitting into a local minima, because this momentum will sometimes knock you over the lip of the local minima, and then you can maybe find a better minimum. So momentum is usually the way that people do it. Okay, so that's it for this section of the talk. We're going to do a little bit more on the practical considerations in the next stage.